Hey everyone, it's Miss Bell here again from the Science Lab, and today we're going to talk about something that's super fun and exciting. This is a tool that we get to use every now and then in the Science Lab, and this tool can do so many fun things. Take a look at this. Look at that! How exciting is that? I wonder how many paper clips are stuck to my mystery tool. Now, some of you might already know what this tool is called and how it works and what all it can do, but I love playing with these. They are so fun. So my tool that we use in the Science Lab is called a magnet. And magnets are so fun to play with and explore with different objects. Now, this type of magnet is called a magnet wand, where I can hold on to it and my magnet is only right here. There are other types of magnets, like this bar magnet. It's kind of a rectangular shape, or it might kind of look like this, a bar magnet, rectangular shape. I also have circular magnets like this, or there's a U-shaped magnet, or it might be called a horseshoe magnet. But all magnets kind of work the same. They differ in how strong or how weak they are, but when we're talking about magnetism, that's just an invisible force all around our magnets that we can't really see with our eyes, and it allows objects to come close to the magnet and stick to the magnet, or it might cause an object to kind of go away from a magnet. When you're talking about magnets, we know that every magnet has two different ends or two different poles. A magnet will have a south pole labeled with an S, and a magnet will have a north pole labeled with an N. Sometimes they're also color-coded. You will see north colored mostly with red, and sometimes magnets have south poles colored with blue. So if I look at my magnet and I turn it this way, the south pole and the north pole. If I turn it this way, the north pole and the south pole. So those are my two poles, or my two ends to my magnet. When dealing with magnets, when something gets stuck to a magnet, that means it attracts to a magnet. And that attraction happens when two opposite poles come together. So on my top magnet, I have the S, or the south pole, facing toward my north pole on my bottom magnet. So I'm going to bring my two magnets together, and when I let go, whoa, it's not magic, it's science that's happening. My south pole is attracted to my north pole, and my north pole is attracted to my south pole. Do you see how they're the same? They come together. I can also totally flip my magnets around, the north pole on top, the south pole on the bottom, and the same type of attraction will happen, because they are pulling toward each other. That's that force. They are pulling toward each other because we know that opposite poles attract. And the opposite thing happens when we have two poles that are the same coming toward each other. So on my top magnet, I have the north pole facing downward, and that is coming close to the north pole on my bottom magnet. So right now I'm showing you north to north. Can I get them to touch? And I'm trying, believe me, I'm trying. But there's something there that just doesn't like it. It doesn't want to connect or come close. Those poles that are the same, they're pushing away from each other. Let me try to turn my magnet around. So I have south next to south. Let's see what happens with this. Here we go. Same thing. I just can't get them to cooperate with me. They are not wanting to connect. In no way are they wanting to attract to each other. And this just shows us that two poles that are the same, whether it's south to south or north to north, they are not going to come together. Instead, they are going to repel away from each other and push away from each other. I want to show you guys how you can make a marker look like it's floating. All you need is some sort of tube, like I have here. It's a clear graduated cylinder and some magnets at the bottom. Over here I have one of those fat markers with magnets on the bottom of it. Now I used tape to tape the magnets together and to tape the magnets to the marker. And that's all I'm going to need with this little demonstration. But let me show you how a marker can float in the air. Are y'all ready? Are you guys ready? Okay, let's count it off. 3, 2, 1. Whoa! Whoa! What is happening? If you look close, there is no touching between the bottom magnets and the top magnets. There's nothing in between. Is the marker floating? Is it levitating? It sure looks like it. I'm able to use my finger and my hand to put a force on the top and it pushes the marker down, but then it just springs back up and it looks like it's bouncing in the air. What is happening? What are we seeing with our eyes? Well, we know that these magnets are not attracted to each other. So it does not have a north to south or north to south attraction. Instead, those magnets are moving away from each other. So they're pushing away from each other. So the top magnet could be south and the bottom magnet could have a south pole facing each other, or it could be a north to north, since the same poles repel away from each other. So I want you guys to watch what happens when I take a Hot Wheels car taped with a magnet on top. Watch what happens when I bring another magnet close to the car. What's going to happen? Is it going to repel or attract? Is it going to push the car away from me or pull the car toward me? You guys ready to see? Let's drive this car. Here we go. If I have a magnet like my U-shaped magnet right here that is not labeled with an N for north or a S for south, there is a way to figure out is this the North Pole or is this the North Pole? And is this the South Pole or is this the South Pole? One way that scientists can figure out which pole is which is if you get another magnet that is clearly labeled north and south. So I'm simply going to put my south pole on one of my edges or my ends of my U-shaped magnet, and I'm going to see, does it attract, so come together, or does it repel, go apart from each other? And this side over here is definitely repelling. In no way do these two sides of the magnet want to come together. So I'm then going to move my south pole of my bar magnet to the other side and see what happens. It is attracted and sticking together to that side of my magnet. And we know that opposite poles attract. So if this is south with my bar magnet, then my bottom magnet has to be north. North attracts to south, or south attracts to north. So if I know that this is my north side, or my north pole, then that only means that over here would be what? It would be my south pole. Because, like I showed before, if this is my south pole and this is my south pole, when I put a south pole next to a south pole, in no way are they going to stick together because they are repelling. If I flip my bar magnet around, I now have a north pole on the top, right? And I know that this is the south pole. So south right here, north right here. What's going to happen right now? They are going to attract. North and south, south and north. That means they are attracting to each other. But if I move it over to this side, north right here and south right here, north right here, then I know that they are not going to stick together because north to north does not attract. Instead, it repels. When I pick up my magnet right here, I'm not able to see any sort of force happening. I'm able to see when something is attracted to it because that item sticks to my magnet, but I'm not able to see any sort of lines of magnetism or magnetic fields, as we call them. Now, they are there, even though they're invisible, and there's a starting point and an ending point, and they always come back to the magnet. So they start at the magnet, they go away from the magnet, and then they come back to the magnet. Our globe right here, which represents our planet, well, our planet could be considered a big, big magnet. And there are invisible magnetic fields working around our planet, just like there's invisible magnetic fields working around my magnetic wand right here. So here I have a bucket of metal nails, and I have my handy dandy magnet wand. I want you to predict what's going to happen when I touch my magnet to these nails. Are they going to stick and attract, or are they not going to stick and repel? What do you think? Here we go. Count it down. 3, 2, 1. Let's see. Whoa! How crazy is that? Look how many stuck to my magnet. That's some strong attraction right there. What would happen if I tried to attach more nails to my magnet? Would I be successful or would I fail? Would my nails have to touch the magnet directly, or would I be able to just touch one of the nails? What do you think? Have you ever done something like this? Have you ever tried to play with nails or screws or bolts with a magnet? As you can see, I'm having lots of fun here in the science lab. I wonder what would happen if I just stuck them to the nails and not the actual magnet. Whoa, that one totally stayed in place. It didn't fall down like some of my other ones did. Whoa, how did that happen? I can take my magnet wands and stick metal nails to it, because I know that whatever material or whatever metal these nails are made out of are attracted to the magnet. They are considered magnetic. And I can build my little link of nails as best as I can, because that magnetism is flowing through my magnet and then through my nails, and I'm able to see how this is able to stick together hopefully without falling. Once the weight gets too much, they're going to start falling down and I can't stick anymore. But I can take my top nail, which everything is attached to, I can pull it off of my magnet and let's see what happens. That magnetism running through the nails is no longer happening, and therefore they are no longer attracted to each other. For this experiment, we're going to take a clear petri dish and pour some corn syrup inside. Now, corn syrup is a liquid. It's really thick and sticky, and it's clear in color. Next, what we're going to do is take some iron filings and pour them kind of in that corn syrup. I'm going to try my best to sprinkle them around like such, and then I'm going to use something to stir them with. Now right now I have a toothpick, and I'm going to try my best to just incorporate all of the iron filings with the corn syrup and kind of spread it around evenly like such. For the most part, everything's spread around evenly. So what I'm going to do next is take my magnet and place it underneath the petri dish, right in the center. And we're going to see what happens when I do that. There's my magnet. I'm going to center it right in the middle and then place it on top. We're able to see the magnet pull on all those iron filings, because we know Iron is one of the metals that is attracted to a magnet. And we can see those invisible lines of magnetism. You can see how they are all being pulled to the center of my petri dish. And even though it's a slow process because they're kind of stuck in that oozy goozy corn syrup, we're still able to visually see those iron filings or those shavings being attracted to our magnet. This time I'm going to stick 3 magnets under my petri dish and speed it up even more so that you guys can see what it looks like. And here I have a bottle filled with water, and I poured those iron filings inside. And I'm just playing around with a couple of magnet wands to see how the iron filings attract to my magnets. You're also able to see those magnetic fields as I'm moving my magnet up and down and all around and in circles as they attract to the magnet and follow the magnet's movement. Magnets are used in a lot of different objects that we see or even use in everyday life. One example might be a can opener, where the top of the can opener has a magnet and it sticks to your can of beans or your can of corn to help open the can. Another example might be a blow dryer, like what I have over here, or a compass that uses a magnet inside to let us know and point to the direction of where the North Pole is. We're able to see where north is. You can see with my compass right now, the red part is pointing to the north. And that uses a magnet in order to show us the direction of where north is going. However, I can counteract that with my magnet as I get my magnet close. I'm able to manipulate my spinner inside because I know that since our red pointer is a south pole and it is pointing toward the North Pole of our planet, that is how we are able to see the north. But since my red spinner part is a south pole, I'm going to attract it to my North Pole right here from my magnet. And I'm able to spin it around and around and around and show you how compasses are made with a magnet inside. Also, speakers inside a computer or speakers inside a phone or even little earbuds use magnets. How about a doorbell? When you push a doorbell at a house or apartment, did you ever think there's magnets in there that help it work? Or sometimes when you go into a kitchen, you might see a strip of magnets on the wall, and there's lots of different utensils stuck to the magnets like knives or spoons or ladles. You might have a purse or a wallet that has little magnetic snaps on it that help them stay closed and together. Or maybe there's doors, maybe to a refrigerator or a freezer or cabinets in the kitchen that when you open it and close it, the magnets help them stay closed together so that they don't open or so that no hot air gets in the fridge. Other items that have magnets might be our cell phones or computers or even iPads and Chromebooks like you guys use in your classroom. When talking about magnets, if you place a magnet close to or next to an object, it's either going to stick to that object or not stick to that object. And there are certain items or materials that do stick and certain items or materials that don't stick. So, for example, this is not sticking, nor is this, nor is this, or this, or this. But if I go like this, those are sticking to my magnet. Or if I go like this, that is sticking to my magnet. Here are some items that I found around the science lab that we are going to test with our magnet to see if they are magnetic, so they attract to the magnet, or they are non-magnetic, meaning they do not attract to the magnet. So here's a pen. I'm going to hold it up to my magnet, and if it sticks, then it would be magnetic, but since it does not stick, it would be considered non-magnetic. Now I'm going to grab my spoon and see if it sticks. Oh, which it does. So we would consider that magnetic. Science is so fun sometimes. Oh my gosh, this is a ball. Whoa! You can definitely have fun with science and play around and experiment and do all different types of fun. Whoa! Did you see that? Did you see that? Oh my goodness, I hope you saw it. I'm going to try to do it again. Who knew that science could be so fun, especially when you're working with magnets? I could do this for days. I can make my magnets dance like this. Boop, 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 boop. Why do you think they're sticking to each other without me ever touching the magnet? Why do you think that's happening? Why do you think some are falling down? Whoa! How cool! While others have no problem with staying attached to other pieces. I'm gonna go for it. I'm gonna try to get I'm gonna try to get every single one of these nails stuck to my magnet. You think I can do it? Yeah, you think I can do it? Okay, here we go. Where do you think Miss Bell should put the last nail? I'm gonna go for right here. Let's see. Let's see if it works. I found a great spot. That's all my nails. I have no extra nails.